First, we'll look at stress and strain in 2D at the macro level and informally. Starting with a rectangular or square plate of elastic material, we can deform it by applying a traction to one of its surfaces. A traction in 2 dimensions has units of force per unit length. So the diagram shows an upward traction tau applied to the top surface of a square plate and the resulting stretching of the plate in the vertical direction, and also the contraction in the horizontal direction. If we apply a downward traction on the top surface, the plate will compress in the vertical direction and expand in the horizontal direction. Thus, a vertical traction produces both vertical and horizontal strain. Note that in all of our systems to date, analysis of the system in the x and y directions was independent, and that is not the case for stress and strain, making for a more complicated analysis and longer equations. A traction can be a normal traction that is perpendicular to the surface to which it is applied, or it can be a shear traction that is parallel to the surface to which it is applied, or it can be a combination of the two. An applied traction has a magnitude in units of force per unit area, which is length in 2D, and a direction, and hence it is represented by a vector. A tensile traction is a normal traction pulling away from the surface to which it is applied, and a compressive traction is a normal traction pushing toward the surface to which it is applied. There are also normal strains, which are tensile or compressive, and shear strains. If a shear traction is applied to a square plate as shown in the diagram, the angle between the x and y axes in the plate will be changed, in this case reduced. This type of strain is called shear strain and is measured as an angle. Hooke's law in 2D relates stress and strain. We will define the notation precisely in slides that follow. For now, we can informally say that sigma xx is normal stress in the x direction, sigma yy is normal stress in the y direction, and sigma xy is shear stress. Also, epsilon xx is normal strain in the x direction, epsilon yy is normal strain in the y direction, and theta, the angle, is shear strain. The parameters of Hooke's law are E, which is known as Young's modulus, P, known as Poisson's ratio, and G, the shear modulus. What does Hooke's law tell us? If a normal traction is applied to the top surface of an elastic object, it will produce a corresponding stress, sigma xx, along the top of the object. If sigma xx is positive, it is tensile, meaning it will stretch the plate upward. From Hooke's law, we have that the stress will cause a positive strain, epsilon xx, that equals 1 over E times the upward stress. Also, there will be a negative or compressive strain in the y direction equal to minus P over E times sigma xx. So the ratio between the horizontal strain produced by a vertical stress is minus P times the vertical strain. Similarly, a horizontal stress, sigma yy, produces a horizontal strain that equals 1 over E times sigma yy, and a vertical strain of minus P over E times sigma yy. Normal stresses do not produce any shear strain, and shear stress does not produce any normal strain. A shear stress, sigma xy, does produce shear strain equal to 1 over G times sigma xy. Now we're going to look at stress in greater detail. The 4 stresses defined at a point in a 2D object are sigma xx, sigma xy, sigma yy, and sigma yx. In this slide, we'll look at sigma xx and sigma xy. To that end, consider a vertical surface in the interior of a stressed object. Now imagine that the surface is a cut and that the object to the right of the cut is exerting a force on the object to the left of the cut due to the internal stresses in the object, and vice versa. The object to the left of the cut is exerting an equal and opposite force on the object to the right of the cut. The x component of the force that the right side of the object is exerting on the left side through the surface dy is sigma xx evaluated at xy times dy. The y component of the force that the right side of the object is exerting on the left side through the surface dy is sigma xy evaluated at x comma y times dy. These equations define sigma xx and sigma xy, which have units of force per unit length. The stress vector at x comma y corresponding to the surface dy is sigma xx times the unit vector I plus sigma xy times the unit vector j. And it equals the traction applied to the left side of the object through the surface dy. The total force applied to the left side of the object through the surface dy equals the stress vector times dy. The same thing applies to the horizontal surfaces. This time the diagram shows both the forces exerted by the object above the surface dx on the object below the cut. These are the positive forces, and the equal and opposite forces that the object below the cut exerts on the object above the cut. The y component of the force that the top part of the object is exerting on the bottom through the surface dx is sigma yy evaluated at x comma y times dx. The x component of the force that the top of the object is exerting on the bottom through the surface dx is sigma yx evaluated at x comma y times dx. These equations define sigma yy and sigma yx, and the units are again force per unit length. The stress vector at x comma y corresponding to the surface dx is sigma yx times unit vector I plus sigma yy times unit vector j, and it equals the traction applied to the bottom of the object through the surface dy. The total force applied to the bottom of the object through the surface dy equals the stress vector times dx. Reviewing the notation. The first subscript of sigma denotes the surface or the orientation of the surface. X denotes the surface with normal vector 1, 0, and y denotes the surface with normal vector 0, 1. The second subscript denotes the direction of the force or traction, x denoting in the positive x direction and y denoting in the positive y direction. Now we want to show that the sigmas form a tensor that maps the unit vector normal to an arbitrary surface centered at xy to the stress vector for that surface. The diagram shows an arbitrary surface dl with its normal n and stress vector gamma. Note that the angles theta, theta 1, and theta 2 are equal, and that the components of n, the normal vector, are cosine theta and sine theta. And from the large triangle, cosine theta equals dy over dl, and sine theta equals dx over dl. We can make the triangle arbitrarily small, so we make it so small that the sigma values can be considered as constant for the triangle, and we don't need to specify x and y where each sigma is evaluated. Since the triangle isn't moving, the forces acting on the triangle must sum to 0, so the x component of gamma times dl, the x direction force acting on side dl, must equal the negative of the x components of the forces acting on the other sides of the triangle, dx and dy. This is equation 1. Dividing equation 1 by dl results in the first equality in equation 2, and noting that dy over dl equals cosine theta and dx over dl equals sine theta, we have the second equality in equation 2. Comparing this equation to the matrix equation at the bottom of the page, we see that the matrix equation calculates the x component of gamma. A similar argument shows that the matrix equation calculates the y components of gamma, and thus the tensor defined by the sigmas does map unit vectors at a point to the stress vector for the surface corresponding to the unit vector. Now consider the torques acting on the control volume, with the aim of showing that sigma xy equals sigma yx. On the right side, we have a shear traction sigma xy times dy, which creates a counterclockwise torque of sigma xy times dy times dx over 2. Again, we will assume that the control volume is so small that the sigmas can be considered constant. Then the torque on the left side of the control volume also equals sigma xy times dy times dx over 2, and it is also counterclockwise, so it doesn't cancel the torque on the right, it doubles it. So the left and right sides exert a counterclockwise torque of 2 times sigma xy times dy times dx over 2 on the control volume. Similarly, the top and bottom sides exert a clockwise torque of 2 times sigma yx times dx times dy over 2 on the control volume. The angular acceleration of the control volume equals the sum of the applied torques divided by the moment of inertia, which is proportional to dx times dy. So the angular acceleration equals 2 times sigma xy minus sigma yx divided by a constant, as shown in equation 1. And since the angular acceleration is 0, sigma xy must equal sigma yx. Now consider all the forces acting on the control volume. The formula for F sub x shows the forces acting in the x direction, consisting of sigma xx evaluated at x plus dx over 2, comma y, at the center of the right side, times dy, minus sigma xx evaluated at x minus dx over 2 at the center of the left side times dy, plus sigma yx evaluated at x, comma, y plus dy over 2 at the center of the top times dx, minus sigma yx evaluated at x, comma, y minus dy over 2 at the center of the bottom times dx. The acceleration of the control volume in the x direction is given by the sum of the x direction forces divided by the mass of the control volume, which equals rho times dx times dy, where rho is the density of the control volume. As per equation 1, the acceleration times rho equals f sub x divided by dx times dy. And since acceleration is 0, the right side of the equation is 0, and taking the limit as dx goes to 0 and dy goes to 0, we have that the partial derivative of sigma xx with respect to x plus the partial derivative of sigma yx with respect to y equals 0. And this is the equilibrium model for stresses in the x direction. A corresponding analysis gives the equation for equilibrium for stresses in the y direction, and we have the equilibrium model for stress.
Love, oh love, oh careless love. I said love, oh love, oh careless love. I said love, oh love. Careless